Hey guys, in this video we're going to do 3 examples using the squeeze theorem, and then we'll do one more complicated one in the next video. But for now, let's go ahead and look at this one. So example 1, it's a pretty direct application of the squeeze theorem, but it's good to look at these sorts of things. So suppose g of x is less than or equal to f of x is less than or equal to h of x for all x in the interval 7 to 19. Okay, so this is the open interval 7 to 19, meaning 7 is less than x is less than 19. So suppose this is true, and suppose that limit as x goes to 12 of g of x equals the limit as x goes to 12 of h of x equals negative 4. Then limit as x goes to 12 of f of x equals what? Well, here, what do we have? We have f being squeezed between g and h, right? F is squeezed between g and h for all x between 7 and 19. Well, 12 is between 7 and 19, right? And g and h have the same limit as x goes to 12, so the limit as x goes to 12 of f of x is going to have to be the same thing, because, again, to reiterate, f is squeezed between g and h for all x between 7 and 19. 12 is between 7 and 19, so the limit as x goes to 12 of g of x and the limit as x goes to 12 of h of x, those are the same thing, and because they're the same thing, and because f is squeezed between g and h, then this limit, automatically we can just say it has to be the same thing. So this is just a direct application of the squeeze theorem. Nothing really crazy or exciting or interesting happening here, but it's good to see this. So you might be wondering, well, in the last video we said f less than or equal to g less than or equal to h. Yeah, it doesn't matter what you call the functions. The only thing that matters is which one's in the middle here being squeezed. So when we talked about the squeeze theorem in the last video, g was the one being squeezed, so it was in the middle. But it doesn't really matter what the order here is, or rather I should say it doesn't matter what we call them, but you just want to look at which one is being squeezed. And in this case, f is being squeezed between g and h. So f is the function that we're going to apply the result to here. Okay, so that's example 1. Let's see one that's a little more interesting here. So this is going to be example 2. And actually, example 2, we're going to end up using this fact few more times possibly. So example 2 here, limit as x approaches positive infinity of sine of x divided by x equals what? Well, how are we going to answer that? So we know how to answer the limit as x goes to infinity of 1 over x, right? We know what that is, that's just 0. But what about sine of x over x? So this is kind of complicated. Well, not really complicated, but kind of tricky. So remember what the sine function looks like if we want to just sketch a graph of that real quick. Here's our x-axis, here's our y-axis. And the sine function kind of sort of looks a little something like this. Wavy, wavy, wavy. Just a rough sketch, not really to scale, but none of my graphs ever are, I guess. So sine function's kind of doing this, right? And as x shoots off to positive infinity, what's the sine function doing? It's just oscillating back and forth, back and forth. It never stops oscillating. So as x goes off to infinity, sine of x, the limit as x goes to infinity of sine of x isn't really defined, because sine of x just oscillates, it bounces back and forth. But what is it bouncing back and forth between? It's bouncing back and forth between 1 and negative 1, right? So actually we know that negative 1 is less than or equal to sine of x is less than or equal to 1, right? We know that. So how's that helpful to us? Well, what we're concerned about is sine of x divided by x. So let's take this and divide everything by x. So if we divide that by x, then we have to divide this by x and divide that by x. So what do we have here? Here's our function sine of x over x. It's being squeezed between these two guys here, all right? And this is actually true for all x. So this is for all x. I guess we should say for all x not equal to 0, because now we're dividing by x, so x is not allowed to be 0. But again, we're taking a limit as x goes to positive infinity, so we don't really care what happens at x equals 0, right? Because eventually we're just going to be really far off to the right, really far away from 0. But anyway, so we have this being true, and what else do we know? We know that limit as x goes to positive infinity of 1 over x equals 0, right? We know that. And what else can we say? Limits as x goes to positive infinity of negative 1 over x. Well, what's that going to be? Well, negative, this negative isn't going to affect anything, right? So limit as x goes to infinity, positive 1 over x is 0. Limit as x goes to infinity of negative 1 over x is the same thing, just 0, right? So what's going on here? We have negative 1 over x less than or equal to sine x over x less than or equal to positive 1 over x for all x not equal to 0. And the limits at infinity of 1 over x and negative 1 over x are both 0. So the squeeze theorem tells us that the limit as x goes to infinity of this guy has to be the same thing, okay? Because the limits at infinity of these two things out here are the same, and this guy is being squeezed between these two guys. So right away that just tells us that this limit here must also be 0. All right. So again, just to recap real quick what happened here. So sine of x over x, we don't really know how to deal with that directly because as x goes to infinity, sine of x just bounces back and forth between 1 and negative 1. But if we use this kind of analysis here, so like we just said, negative 1 is less than or equal to sine of x is less than or equal to 1 for all x, right? And now we can divide everything by x and say this. And now we have to make the restriction that x is not equal to 0. But again, that doesn't really matter. And now we have our function sine of x over x pinched or squeezed or sandwiched between these two guys here, okay? 1 over x and negative 1 over x. And the limits of both of those guys as x goes to infinity are 0. Therefore, the squeeze theorem automatically tells us, just directly right away, that this limit also has to be 0. Okay? So that's example 2. Let's go ahead and look at one more example that's kind of similar to this, but slightly different. Actually, it's probably a little simpler. But example 3. So let's find limits as x goes to positive infinity of cosine squared x divided by x. Oh, by the way, in example 2, if we took the limit as x goes to negative infinity instead, we would have had the same result in example 2. And actually the same thing will be true here. Whatever result we get here, it's going to be the same thing as x goes to negative infinity. But hold that thought for now. So let's see, what would this be here? Well, we have the same kind of problem. Limit as x goes to infinity. What does cosine squared x do? Well, cosine squared, kind of a goofy function, but let's just think about plain old cosine for now. So, x-axis, y-axis. So what does cosine do? Well, the cosine function, it's pretty much just like the sine function, but starts at a different point. So cosine is going to bounce back and forth like this, right? Cosine's doing something like that. Here's y equals cosine x. But what we're looking at is cosine squared. So cosine squared, if you take something and square it, you're going to get something positive or 0. So cosine squared is actually going to follow the same path here, but cosine squared doesn't become negative. So it's actually going to bounce back up like this, and then up like that, and then up like that, and so on and so forth. Okay, it's just going to keep doing that. So here's y equals cosine squared x. So if we look at just cosine squared x, what do we see here? We see that 0 is less than or equal to cosine squared x is less than or equal to 1 for all x. Okay? But our function in question here is cosine squared x divided by x. So what we're going to do here is take all three of these guys and divide them by x. So this is the function we're concerned with here, cosine squared x over x. So divide this by x also, and then divide that by x. And now because we did that, we have to make the restriction that x is not equal to 0. But again, we're taking a limit as x goes to positive infinity, so we don't really care what happens close to x equals 0. All right, so that's okay. So we can actually simplify this a little bit, right? 0 divided by x is just 0. So actually we could just say this. Right, and that's good. So how's that help us? Well, now, what's the limit as x goes to positive infinity of 1 over x? Well, like we just saw earlier, and we've done a few times before, it just equals 0, right? Now, how about the limits? So that's the limit for this guy. What about the limit for this guy? Limit as x goes to positive infinity of 0. Well, 0 is just a constant, right? So the constant 0 has nothing to do with this x. So we can shoot off x to wherever we want, okay? But 0 is just going to stay 0. Alright, so the limit as x goes to infinity of this guy is 0. Limit as x goes to infinity of this guy is 0. And as x goes to infinity, we know that this guy is squeezed between these two guys. So right away we can just automatically say that the limit as x goes to infinity of the guy being squeezed must also equal 0. Alright. So you might be wondering, could we also have said -1 here instead of 0? Yeah, actually you could say that. That's still true, and it would still work out in this case, but sometimes this isn't really the tightest bound that we can have. Okay, yeah, this is true, but 0 is a better bound to use, and sometimes for more complicated examples with the squeeze theorem, you might need a tighter bound, or you might have to find the tightest bound that you can. So yeah, this is true, and luckily it'll still work out in this case, but we could do better and say, instead of -1, we could do better and say 0. But again, in this case it doesn't really matter too much because you'll get the same result, but in general, you should try to find the tightest bound you can and then apply that. And if the squeeze theorem doesn't work in that case, then you might have to try something else. But for now, let's just focus on the squeeze theorem. So in the next video, we'll do one more example that's a little more complicated, but it'll use these results.